Hi and welcome to John's Maths Book. In this video, we're going to be finding the volume of non-rectangular regions using double integration. If you like the video, then please hit the like button, and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. We saw in an earlier video how to calculate the volume under a curved surface using double integration. In that video, the curved surface had a rectangular base, and we found the total volume by integrating between fixed intervals on the x and y axis. In this video, we're going to extend this by calculating a section of the volume under a curved surface. Instead of having a rectangular base, this time it will have a triangular base, and the upper limit of one of the intervals of which we integrate will be a function. If you haven't already watched the first video in this series, I urge you to do so, as we will build on knowledge gained from this video. I will post a link to this video in the section below. On the left, we have a curved surface. I've shaded a section of the curved surface in pink and projected this down onto the XY plane. As you can see, it creates a triangular shape, which I've shaded in blue. So our goal here is to find the volume under the pink shaded region bounded by A on the x-axis and B on the y-axis. We know from our previous video that the curved surface is a function of x and y as it has a height component. We can write this as z is equal to f of xy. For values of x and y, we get a height component, which equates to the point on the surface. However, in this case, we are only interested in the points on the surface that are bounded by the pink region. So let's take a fixed point on the x-axis and an infinitesimal slice dy on the y-axis. F of xy dy will give us a small slice of area indicated by the dark stripe on the blue shaded region. If we now sum all these slices, we get the area of the blue shaded region. We do this by integrating in the y direction starting at 0. When we had a rectangular base, our upper limit of integration was a constant. In this case, however, the upper limit will be variable and a function of x. Let's see how we get the upper limit of integration in this case by extracting the base of our triangle in the xy plane. If we now look at the equation of the line formed when we join point A on the x-axis to point B on the y-axis, we see that it is y is equal to minus b divided by a times x plus b. So our upper limit of integration here is y is equal to minus b divided by a multiplied by x plus b. What this means is that for each infinitesimal slice of area, so for different values of x, one of which is shown by the blue shaded region, the upper limit of integration on the y-axis will be variable. So we need to express it as a function of x. Once we've evaluated this integral, we will have a single slice of area expressed as a function of x. We can then sum the slices of area by integrating along the x-axis this time from x is equal to 0 to x is equal to a. This will then give us the slice of volume under the pink surface that we are looking for. So now we know how to work out the volume. Let's look at a real example. So we have the function z is equal to 2xy, and we have limits on the x-axis from 0 to 1 and limits on the y-axis from 0 to 1. So let's calculate the volume under this surface. So firstly, we need to integrate in the y direction from y is equal to 0 to y is equal to minus x plus 1. If you think in our original example, we had y is equal to minus b divided by a times x plus b. Well, in this case, a and b are both equal to 1. So the upper limit is the equation of the line that we saw in our previous example. So that is y is equal to minus x plus 1. So if we integrate this, we get 2xy squared divided by 2, and the upper limit is minus x plus 1 and the lower limit is 0. So we note that the 2's will cancel out, and if we put in our upper limit, we get x multiplied into minus x plus 1 all squared, and our lower limit is minus 0. So next we need to integrate in the x direction between 0 and 1. Now I've expanded that out to give x cubed minus 2x squared plus x. And now if we integrate it, we get
x to the power of 4 divided by 4 minus 2x cubed divided by 3 plus x squared divided by 2 between the interval of 1 and 0. If we plug these numbers in, so starting with 1, we get a quarter minus 2/3 plus a half. And if we put in 0, we get 0. So a quarter minus 2/3 plus a half is equal to 1/12, which is our answer.